All right, so then before we get started on working through any exercises, we'll just go over a few facts about the trig functions that we're going to need to know. Yeah. So in particular, there's a couple values of the trig functions that you need to know. So let's start by talking about cosine, sine, and tangent. And so you definitely need to know the values of sine, cosine, and tangent at the angles 0, pi over 6, pi over 4, pi over 3, and pi over 2. So these are all the angles in the first quadrant that you need to be, I guess that you'll need to know. And then here, let me just kind of list the values of sine, cosine, and tangent at each of these angles. So sine of 0 is 0. Sine of pi over 6 is 1/2. Sine of pi over 4 is square root of 2 over 2. Sine of pi over 3 is square root of 3 over 2. And then sine of pi over 2 is 1, okay? For cosine, cosine is kind of just the reverse of sine. So it starts at 1, and then it's just going to go backwards down to 0 at the end. Finally, for tangent, so tangent, if you just know sine and cosine, then in theory, you could always figure out tangent by using the fact that it's sine over cosine, okay? So once you know sine and cosine, you can figure out all the other trig functions, really. But that said, it takes a little bit of time to work out what tangent will be in terms of sine and cosine. So I think it's best to have tangent memorized as well. So tangent starts at 0. Tangent of pi over 6 is root 3 over 3. Tangent of pi over 4 is 1. Tangent of pi over 3 is root 3. And then tangent has a vertical asymptote at pi over 2. And so it doesn't have a value there. You can maybe say it does not exist, tangent of pi over 2, okay? So this is kind of, in my opinion, I would say this is kind of the bare minimum of what you need to have memorized. I don't necessarily have many good tips per se on how to memorize it. There's one kind of pattern that I think could maybe help you in memorizing sine and therefore cosine as well. Which is the following pattern that I guess I kind of noticed before. So these values of sine that we have 0, 1/2, square root of 2 over 2, square root of 3 over 2, and then 1. So those are actually equivalent to, so 0 is the same as square root of 0 over 2. 1/2 is the same as the square root of 1 over 2. Oh, well. And then you've got square root of 2 over 2. And then square root of 3 over 2. And then square root of 4 over 2. Well, square root of 4 is 2. So this is 2 over 2, and so it's equal to 1, okay? So therefore, these values of sine that are listed in the table, they have this pattern where it's square root of 0 over 2, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, and then square root of 4 over 2, okay? We've just simplified 3 of them and written them more simply in the table. But that's kind of one way that I think could be helpful to memorize it, if you just remember this pattern in the numerator. That can give you sine, and then just remember that cosine is kind of sine but reversed. Any questions so far about that? Okay, all right. Now, as I was saying, these angles, these are the angles that are in the first quadrant that you need to know. And so then to figure out the values of sine, cosine, and tangent and the other quadrants, then you can figure the rest of those out by looking at the unit circle. And so if you know that, let's say as an example, let's look at the angle of pi over 6. Okay. So we know that sine at pi over 6 is going to be 1/2, okay? And if you'll recall, when you're looking at the unit circle, the x-coordinate of the point on the circle represents the cosine of the angle, and the y-coordinate represents the sine of the angle, right? Okay. So keep in mind that cosine represents the x-coordinate and sine represents the y-coordinate. That helps you keep track of where which one is positive and where which one is negative. So looking at the second quadrant, so if we go out an angle pi over 6 up from the negative x-axis, so this point, you can see that it's going to have the same y-coordinate as this point, but the x-coordinate becomes negative, right? So since the x-coordinate is negative in the second quadrant, you know that cosine will be negative. On the other hand, sine is the y-coordinate, so in the second quadrant, the coordinates are still positive. So that's how you know that sine will be positive in the second quadrant. And by virtue of tangent being sine over cosine, you can then figure out tangent is negative in the second quadrant as well. Okay. And then this angle that we're looking at here right now, so I guess it has the same reference angle of pi over 6. Okay. But the actual angle measure, if you measure from the positive x-axis, do you know how you would figure out the actual angle measure if its reference angle here is pi over 6?
Subtracted from
Yeah, I think I heard that right. So keeping in mind that the negative x-axis is at an angle of pi, you can do pi minus pi over 6 to figure out this angle measure. Pi minus pi over 6 will give you, I guess, a 5 pi over 6. And so that means this represents the angle of 5 pi over 6 in the second quadrant. And so we can say that sine of 5 pi over 6, okay, it should also be positive 1/2 still, because the y-coordinate is still positive. But if you're looking at cosine of 5 pi over 6, well, let's see, cosine of pi over 6, if we remember that was square root of 3 over 2. Cosine becomes negative in the second quadrant, so it's now going to be negative square root of 3 over 2, okay? So it takes a little bit of work. If you know only the first quadrant, if you only have that memorized, it takes a bit of work to figure out the values of the trig functions in the other quadrants, but you can do it if you just like draw a picture of the unit circle and try to use like the symmetry to figure things out, okay? Me personally, it's kind of my job to work with these things. So if you work with it enough, you're gonna memorize it, even if you're not trying to memorize it. So my only other suggestion to help in memorizing is to just maybe practice more, work with this material more. You'll, of course, naturally just pick up on it if you do that. Okay? All right. Was there anything else that you might have wanted to ask me before I maybe just get started on working through some problems? Okay, all right. Well, I'll go ahead and just, yeah, no problem, okay? I'm gonna go ahead and start working on some problems. If that's all you wanted to ask, you're welcome to leave at any time, really. But if you stick around, feel free to ask me questions at any time. I'll try to check the chat regularly, okay? All right. So I'll get started on working through some of the graphing problems. Okay. All right. So I'm going to start with problem number 2, I think. So for problem number 2, we have the function f of x equals 2 cosine of x over 3 plus pi over 2. Okay. So we want to graph this function and then also ask for the amplitude and the period. Okay. So amplitude and period are pretty easy, so let's cover those first. Okay. So for cosine and sine, if you have a sine or cosine function of one of these two forms, yeah, okay. In general, the amplitude is going to be the absolute value of a, where a is the coefficient of the cosine or sine. So yeah, in this case, the amplitude is going to be 2, because 2 is the coefficient of the cosine that we have here. All right, good, okay. Yeah, so in general, the period is going to be 2 pi over b, where b is the coefficient of the x. So here, the coefficient of the x is 1/3. So the period would be 2 pi over 1/3. So that would be 2 pi times 3. So yes, the period ends up being 6 pi. All right, great. Okay, so now we want to actually work on graphing this function. And so the way that you guys usually graph trig functions is you sort of make a table, right? And personally, I think this is a great way of doing it as well. So that's how I'll graph the trig function. So here's how it works. What we're going to do is we're going to start by treating the argument or the inside of the cosine as like a single quantity. So we've got x over 3 plus pi over 2. Okay. All right. Okay, now we know that cosine has some nice values at 0. Well, let's see here. We know a lot of values of cosine, but for the purpose of graphing it, it's usually good enough to just look at the pi over 2 angles. So starting at 0 and going up by pi over 2 each time. All right. So right now, if I graph some angles from 0 to 2 pi, that's going to be 1 period of cosine. So this problem did ask for 2 periods. So if you wanted to go out even more, you can continue adding pi over 2 to each of these values. Yeah, and you could go up to 4 pi, for instance, in order to get up to 2 periods, okay? All right. So we list some of the values of cosine that are very convenient. So then we know that cosine of 0 is 1. Then cosine hits 0 at pi over 2. Cosine of pi is -1. So here, this is where some memorization helps, right? Cosine of 3 or pi over 2 is 0. And then 1. And then here, it's just going to repeat. Okay. Great. Okay, now, here what we've done in the table of those, we have the inside of the cosine plotted out versus cosine, but ultimately what we need is x versus our function, right? So we need to do a couple of things. One thing I'll do first is we do need to multiply our cosine function by 2. Okay. So then what you want to do here is multiply all of your cosine values by 2 now in order to have the values of your function plotted out. So here what I'm going to do is just multiply everything by 2 in this column. Okay. Okay, so then the red gives us the values of our function, but we need to compare that with the x values. So now what we need to do then is kind of work backwards from here we have x over 3 plus pi over 2. And I sort of just want to do some algebra and work my way back to x. So what I would do first probably is just subtract pi over 2 from everything to get it in terms of x over 3. Okay. So that means we have to subtract pi over 2 from each of the values in this column now. So here is 0 minus pi over 2. Pi over 2 minus pi over 2. Pi minus half a pi gives you half a pi. All right. So then subtracting pi over 2 from everything in this column. Okay, great. Now we're almost done, but this column represents the values of x over 3. So to get the values of x itself, we would now need to multiply everything in this column by 3 in order to solve for x. All right. Okay, so here it's -3 pi over 2. 0 multiplying by 3. Okay. All right. So then with that, now we have the values of x tabulated, as well as the values of our function tabulated, okay? And then with that, we can plot some points on a graph, and then roughly connect the dots in order to get a picture. Let me try to zoom out a bit. All right. So I'm going to get my graph started here. Now, here in the problem, the instructions for the graph, 2 periods. So I have 2 periods starting at negative 3 pi over 2 for x. And here I just kind of I'm just drawing it by hand, so I'll just arbitrarily mark a place, which I'll call negative 3 pi over 2. And then the next x value was 0. And then we've got 1 at 3 pi over 2, 3 pi, 9 pi over 2, 6 pi, and we have 15 pi over 2, next one was 9 pi, and then we had one more, which was 21 pi over 2. So I've plotted all the x values that we had in the column. Okay. And then the values of my function are ranging between 2 and negative 2. So let's say maybe 2 is up here, and so negative 2 is about down there. All right. So then at negative 3 pi over 2, our function should be equal to 2 to start with. So I'm going to start up here. Okay, now when x is 0, the function should be 0 as well. So I'm going to go down to the origin next. And then when the x is 3 pi over 2, we hit negative 2. So then I'm going to continue going down to there. All right, and then it's just going to kind of continue like this, because we know that sine has this kind of shape like that. Okay, and then I'll connect these next. All right, and then a little bit more here to finish off the periods. All right, there you go. So then that's going to be a rough sketch of the graph of our function. All right, so any questions about that? Okay, great, all right. Did you want to take a look at any other graph problems? There's a tangent and a secant in the review. If not, we can take a look at some of the other parts as well then. All right, great. Let's look at the secant one, okay? Okay. So secant, this was problem number 5 in the review. So I have f of x is 3. Oh no, never mind. It's a secant of 3x plus pi over 2. And then minus 2. So in the review, we asked for a couple of things. We asked for the period as well as the range. Of this function. And then we also asked for the equations of at least 3 vertical asymptotes. And then, of course, graphing 2 periods as well, okay? Okay. So let's talk a little bit about the graph of secant right now, as well as the period range and where the vertical asymptotes will be. So I'll talk a little bit generally first, and then we'll come back to the specific problem. Okay. Let's just kind of briefly look at what the graph of secant is. Do you know sort of an easy way of getting the graph of secant? Like, do you have like a way to memorize how to get it?
I just graph the cosine graph first, and then wherever I see zeros, I kind of just know that's where the asymptote.
All right, no, that's perfect, right? And then to get the graph, you sort of take the graph of cosine, you almost sort of like flip it somewhat upside down, I guess. All right, good. So maybe what I'll do is I'll kind of lightly graph out what cosine looks like. So the graph of cosine looks something like this. Okay. So it has zeros at pi over 2, 3 pi over 2, negative pi over 2, negative 3 pi over 2. So any like odd integer multiple of pi over 2 that's where all the zeros of cosine are. So 5 pi over 2, 7 pi over 2, and so forth. So yeah, for secant, that's where all the vertical asymptotes will be. Okay. And then to get the graph in between the vertical asymptotes, you can take this, sort of looks like a parabola shape, and just kind of like flip it upside down. So it's now going to open upwards like that. For these two on the left and the right next, those, if you sort of flip it upside down, it's not going to open downwards like this. Okay. And then it would just sort of repeat that pattern in every single one of these little strips, okay? All right. Okay. So then for like the regular, like ordinary plain secant function, you can see that its range, it starts at, so there's 2 parts to the range. Yeah. So its range will include everything negative, starting at -1 and going down to -infinity, as well as everything started at 1 and going up to infinity. So you might write that in the sort of interval notation like this: -infinity to -1, union 1 to infinity. Okay. And then it's missing the numbers like in between -1 and 1 in the range, okay? Its period is going to be 2 pi, just like the regular cosine function. All right, but it may help to just kind of have like a general formula for everything. So we have something of the form like secant bx plus c. Well, Not that it matters, but it might look better to write it as minus. Plus d. And I guess this is maybe about the most general secant function you could possibly see, I would like to think, at least in this class. So for this secant function, if we want to know what would its period be, so the formula for the period is the same as for cosine. It's 2 pi over b. B is the coefficient of the x. Now, maybe don't be fooled by the a though, so it's maybe worth noting that there is no amplitude for secant functions, right? Because you can look at the graph and see that like there's no like peak or trough in the graph. It just goes up and down forever. So no amplitude for secant functions. Let's figure out what the range and the vertical asymptotes would be. So do you know how to find the vertical asymptotes? Like in general, like how would you describe the procedure for getting the vertical asymptotes? Yeah, if you can, yeah.
I think it's just like you said, like that any over two taking into consider it.
Okay, all right. So I think I heard a little bit of that. So it's kind of on the right track from what I heard. So you want to use the idea that secant has, like ordinary secant, has the vertical asymptotes at any like odd multiple of pi over 2. So then for this more general secant function, we can say that it will have a vertical asymptote whenever its argument, which is the entire bx minus c, whenever this is an odd multiple of pi over 2, then you should have a vertical asymptote. Now, I guess there's a couple of ways of doing this. So in my problem in the review, we were looking for 3 consecutive vertical asymptotes. So what you can do is kind of list like 3 consecutive vertical asymptotes for the ordinary secant function. Okay. Yeah, so for secant negative pi over 2, pi over 2, 3 pi over 2, that's 3 consecutive vertical asymptotes. And then what you'd want to do is you'd want to take this now and basically solve for x. So you'd add c to everything. And then you divide everything by b in order to solve for x. And then this would give you the equations of 3 consecutive vertical asymptotes by doing that. Okay. And so this is maybe not too important. Like I guess the expressions that I'm writing out right now are maybe not too important, but what is important is that you understand at least the procedure that to find the vertical asymptotes, you can take whatever was inside your function and then set it equal to where the vertical asymptotes of the, I guess, of the original function are. So here, like, the original function that we were looking at was the secant function. And then what you do is you solve for x. And once you've solved for x, you would have the equations of some vertical asymptotes from that, okay? Okay. Now, here I did 3 consecutive vertical asymptotes, but are you guys sometimes asked to maybe find like a general formula or like a general expression for the vertical asymptotes?
100% sure.
Okay, all right. Maybe I'll talk about that. It won't take long, so let me do that as well. So if I wanted like a general formula that represents like all of the vertical asymptotes, instead of writing out a few specific ones. Okay, so for secant, we had this idea that its vertical asymptotes are at every like odd multiple of pi over 2. It's like 1 pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, and so forth. So what you want to do then is come up with a general expression that represents an odd multiple of pi over 2 to use on the right over here. And then you have a couple of options for that. One way to always have an odd number is to take an even number and then add or subtract 1 to it. So for example, if n represents an integer, then if I multiply by 2 and add 1, I know that's going to give me an odd number. So then I might take the inside of our function and set it equal to this. So this would represent like an odd number multiple of pi over 2. And then n would just represent like any integer. Okay. And then from here, you can do the same thing and solve for the x to get the equation of the vertical asymptote, okay? But I guess the key, if you're looking for like a general equation for the vertical asymptotes, is take the inside of your function and set it equal to just like a general expression for where all the vertical asymptotes would be. So for secant and tangent, they have vertical asymptotes at the odd multiples of pi over 2. If you had sine or not sine, but if you had cosecant or cotangent, then they have the vertical asymptotes at every multiple of pi, so it's a bit nicer. You would just take the inside of the function and set it equal to n pi instead. And then you could, again, do the algebra to solve for x. In order to get the general equation for the vertical asymptotes, okay?
Yeah, I was just going to ask, could you just scroll down to sine and the cotangent?
Yeah, there you go. Yeah, okay. All right, and so are you good with that right now? Okay, all right. Let's see here. So with that in mind, let's just look at our problem to practice like a specific example now. Oh, it's not updating, huh? What if I try searching? Okay, there we go. All right. So for this particular problem, let's maybe, oh, okay, yeah, and then also the range. Let's look at that as well in this example. Okay, so in this problem, so remember that for the period, it was 2 pi over the coefficient of x. Okay. So it's 2 pi over the coefficient of x for secant and cosecant, as well as sine and cosine. Let's do the vertical asymptotes next, since I just talked about that. So if I want the general equation, what I'll do is I'll take what's inside the secant expression right now. So 3x plus pi over 2. And I set it equal to an odd multiple of pi over 2 for secant. Okay. All right. So then I need to solve for x now. So I'll minus pi over 2 on both sides first. Okay. And then I could divide both sides by 3 to solve for x. Maybe one thing I'll do first, though, is let's go ahead and simplify a little bit. I have a common denominator. So if I combine the numerators together, okay, and the numerator, if I distribute the pi, we have like 2n pi, and then plus pi, and then minus pi. So we can actually cancel out the minus pi with like the plus pi that you would get. So that will leave us with 3x is 2n pi over 2. Oh, so it simplifies even more. You can cancel out the 2's next, right? So 3x is n pi. So solving for x, you would get x equals n pi over 3. Again, n represents like any integer. So this will give you all of the vertical asymptotes for our secant function. Okay. All right. And then if you specifically wanted 3 consecutive vertical asymptotes, what you could also do at this point is just plug in 3 consecutive integers to get 3 consecutive vertical asymptotes. Okay. 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 All right. Inverse functions. Oh yeah. Okay. All right. So that gets us the vertical asymptotes. Let's see. Should I? All right. So let's have a little bit of a vote right now, since we've got a couple more people. So you know, for these reviews, I usually just see what you guys want me to cover. So right now, I was kind of in the middle of graphing secant. Would you guys like to see me continue that, or would you guys like me to move on to the rest of the review as well? Okay, all right, and just wanted to kind of check on that. All right, let's have a vote. Who wants me to? Okay, sounds good. All right. That's I think that's already majority rule. Okay. All right, so that was the vertical asymptotes. Let me see, what else did we have to do? We got the vertical asymptotes, we got the period. Let's talk about getting the range of this function next, okay? Now for ordinary secant, we talked about how, I did it up here actually, okay. So just for like a plain secant function, its range is everything from minus infinity to minus 1, as well as everything from 1 to infinity, okay? Now for the secant function though, we have this minus 2 out front, which we know that's going to shift everything down by 2 units, right? In the graph. So that means the graph of this function is ultimately going to start at -3 and open downwards. This would shift down to -1 and then open upwards. So then the range of this function would basically be shifting the range of the ordinary secant function down by 2. So we could say the range would be minus infinity, but it would only go up to -3 since the -1 shifted down by 2. And then we would union, oh, whoops, and that should be a closed bracket. And then union, and then instead of starting at 1, again, because of this vertical shift downwards by 2 units, we would now be starting at -1. And then we'd work our way up to infinity again, okay? So that's how you could figure out the range of, say, a secant function. If you just keep in mind what the range of the original secant function was, and then if there's a vertical shift, you can incorporate that vertical shift into the range, okay? All right. So then the last part of this question was to sketch it. Let me sketch maybe one period of this function right now, and then we'll move on to something else afterwards. I'll continue down here. Okay. So to graph this function, so we'll follow the same strategy that we did in the previous example. Okay. Now for secant, to get a sketch of it, I guess it's good enough to just know where the vertical asymptotes are going to be, as well as where, I guess they sort of look like parabolas, not quite, but I'll call them parabolas anyways. You would also want to make a note of where these parabolas are going to start, okay? Okay. So for the ordinary secant function, to plot one period, let's go from -π/2 to 3π/2. Okay, so that's, we've got some vertical asymptotes in between. Okay, yeah, so looking at that picture, I think it'll be appropriate to start looking at when the argument of our secant function is negative pi over 2, 0, pi over 2, pi, and I'll go up to 3 pi over 2 right now. So that should have been 1 period. Okay. And then we know that secant has the vertical asymptote starting at minus pi over 2. But then when the argument is 0, secant is equal to 1. And then it's going to open upwards. And then we have another vertical asymptote here. And then here it's going to look kind of like a parabola starting at negative 1, opening downwards. And then we have another vertical asymptote, okay? Okay. But there's a couple of things we have to do to actually plot our function. So first is our function had a vertical shift of minus 2 built into it. So then I'd want to subtract 2 from all the values in this column. So I'm going to subtract 2 from everything. Of course, you still have a vertical asymptote at these locations, though. Okay, so now that column in red represents the values of our function itself. But then we need to compare our function versus x. And right now we have a compared versus this whole expression, the argument of our function. So what we also have to do here is kind of work backwards from this to solve for x. Solve for x, I'd want to subtract pi over 2 from everything first. And then after I fill out that column, we'll also need to divide everything by 3, or if you will, multiply by 1/3 in order to solve for x, okay? So let's work on that next. We'll work with this column first. So what I'm doing here is I'm subtracting pi over 2 from every number in this column in order to fill out this column. So minus pi over 2 minus pi over 2 will be minus pi. 0 minus pi over 2 will be minus pi over 2. Pi over 2 minus pi over 2 will be 0. Okay. And then just continuing to subtract pi over 2 from everything. Okay, so we have that column filled out. And then now from this column, we're going to multiply every number here by 1/3 in order to get the values for x. So minus pi over 3, and then minus pi over 6, and then 0, pi over 6, and pi over 3, okay? All right. So now that I have the values of x plotted out in this table, I can use my x values and my function values in order to discuss some of the graph now. Let's see here. So I guess I have x going from minus pi over 3, minus pi over 6, 0, pi over 6, and pi over 3. Okay. So we've got a vertical asymptote to start with. At minus pi over 3. We've got a vertical asymptote at 0. And then the vertical asymptote at pi over 3 as well. Okay. Now at minus pi over 6, our function should be equal to minus 1 there. So let's say that's minus 1. So we should be starting here, and then for this first one, the secant function opens upwards. So it'll be something like this. Okay. And then for the next one at pi over 6, our function should be down at -3 now. So let's say that's -3. We're going to be down here. And then for secant, this next one is going to open downwards. So like that. Okay. And that would be one period. So then if you needed to sketch more periods, you could work out a couple more values for x and the function in the table. If you don't need to be that precise, you can just sort of mimic the picture that you had. Okay. All right. So any questions about that? Okay. All right. So then I see a request to talk about the inverse function. So let's do that next. Ah, yes, it is. Yeah. I personally think that's kind of the best way that I've seen anyone graph trig functions before, is using the table. So I really like how your professor does it. Yeah. It takes a bit of work, but it just makes it easy though, so it's nice. Okay. Yeah, let's talk about the inverse trig functions next. And so I guess let's go through each of them. Maybe I'll start with the sine and cosine functions first. Okay. So the inverse sine function, which people also call or write as arcsine. Okay. Now, maybe just a quick note, because I know lots of people get this a little bit confused. So you'll see this notation that's sine to the -1 for the inverse sine function. So it's important to note that it's not the same as raising it to the power of -1. So this is not representing like 1 over sine. Okay. So it's not actually raising it to a power of -1. It's just denoting the inverse of it. Okay. The inverse as a function. All right. So let me talk about what the inverse sine function does. So the inverse sine function, what it does is you input a number x into it, and what the arcsine function does is it outputs an angle. Okay. And the angle that it outputs is the angle where the sine of that angle would be equal to x. Okay. And then for arcsine, there's a restriction on things. So for the domain, the input x has to be restricted between -1 and 1, okay? The reason why is because that was the range of sine, okay? So remember how the range of a function becomes the domain of its inverse? As for the range of the arcsine function, so we put a restriction on the range, or rather on this angle that it outputs. So we restrict that angle data to be between minus pi over 2 and pi over 2. That's somewhat of an arbitrary choice, but that's what people do for arcsine in particular. And because of that convention, that makes the range of the arcsine function minus pi over 2 to pi over 2 then, okay? So then this is the domain and range for arcsine. All right, so let's talk about the arccosine next. So arccosine is similar, but its range is different though. Okay. So then just a kind of a note again, what does it do? Arccosine returns an angle data. The angle data that it returns is the angle for which cosine of data will equal x, okay, whatever you input it. And then there's also a restriction on the angle that cosine outputs, or arccosine outputs. And this is just a convention that people decided to follow, which is that the angle data that it outputs will be between 0 and pi for arccosine, okay? All right. So then the domain of the arccosine function, it's also going to be minus 1 to 1, since that was the range of cosine. But then for the range of the arccosine function, or the inverse cosine, we have chosen, just like as a community, I suppose, for the range to be between 0 and pi specifically, okay? All right. So that's arccosine. Let's talk about arctangent next. Arctangent or tangent inverse. Okay. All right, so inverse tangent, just like all the other inverse trig functions, what it does is it outputs an angle. So specifically for inverse tangent, the angle that it outputs is the angle for which tangent of that angle is equal to x. And then for inverse tangent, the restriction that we put on the angle is that we restrict it to be between minus pi over 2 and pi over 2. Okay. All right. So because of that restriction on the angle data, its range would be ultimately minus pi over 2 to pi over 2. Now for the domain of the inverse tangent function, its domain is going to be all real numbers. And that's because the range of tangent was all real numbers. So then that changes into the domain for the inverse function, okay? It might be useful to see just a little picture of a graph next to each of them. So for arctangent, this is what its graph is going to look like. So arctangent has horizontal asymptotes at pi over 2 and negative pi over 2. And then it's going to look like a tangent function kind of, but it's kind of flipped around, so it'll look like this now, okay? That's what graph of arctangent looks like. All right, so again, you can kind of see its domain is all real numbers. And then the range being minus pi over 2 and pi over 2 is kind of because of these horizontal asymptotes that you had there, okay? Okay. If I were to give maybe a rough sketch of arc cosine, so arc cosine would look something like this, okay? So its domain is specifically minus 1 to 1. And its range is 0 to pi. Okay. So it starts at pi when x is negative 1, and it works its way down to 0 when x is 1. And then let's see here. Ordinary cosine looks like what? Between 0 and pi, it looks like that. So then I want to flip it. So maybe something like this. Okay. So it will look roughly something like this, I want to say, all right? But yeah, it starts up here and it goes down like that. And the arc sine would be kind of similar. Let's see here. So its domain is also minus 1 to 1. But its range is pi over 2 to negative pi over 2. So arc sine is actually going to start down and then work its way up, okay? And let's see here, what does sine look like? Sine would look like, oh, that kind of. Oops, I would sort of flip it. I want to say maybe something like that. But roughly, it starts down here and it works its way up is kind of what it's going to look like, okay? So I think it looks something like that. All right, but that's the domain and range though for each of the 3 inverse trig functions, inverse sine, inverse cosine, inverse tangent. We could talk about the other inverse trig functions, but I feel like most people don't touch them, although you certainly could. All right. So then, do you guys have any questions about any of that? And then maybe would you like to see me talk about the remaining inverse trig functions as well, their domain and their range? Okay, all right. Let's go ahead and finish those up. All right. Oh, oops. So then I guess the next one we would do, well, it doesn't matter, but let's do secant inverse next. Which then some people might write as arcsecant then. Okay. Okay. So the inverse, so again, all the inverse trig functions kind of work the same way in that what they output is an angle. So arcsecant will output the angle theta, for which secant of theta will be equal to the x value. And then secant is, if you'll recall, that secant was 1 over cosine. So since it's 1 over cosine, it has vertical asymptotes. Okay. So then I guess the restriction that we will put on theta would be minus pi over 2 to pi over 2. But not including those two because secant has the vertical asymptotes at those locations. Okay. So then let's talk about the domain and the range. So then I guess the restriction that we decide to place on the angle essentially characterizes the range. So the range should be minus pi over 2 to pi over 2 then. Now, remember that the domain of the inverse trig functions, you can always figure out as being the range of the regular trig function, okay? So do you guys remember what the range of the secant function was? I think you guys are thinking about, oh, okay, yeah, there you go. Yeah, so the domain of the, the range of secant. So if you guys kind of remember roughly what the graph of secant looked like, let's see here. I'll plot it over here to the side real quick. Yeah, so if you guys might remember, secant looks something like this, right? Well, I guess it depends on which one you decide to look at. Yeah, but it looks something like that, okay? Vertical asymptotes at the pi over 2s. Oh, okay, yeah, I see. So for secant, for ordinary secant, its range is minus infinity to minus 1, then union 1 to infinity. So the range of the ordinary secant function becomes the domain of the inverse secant. So this would be minus infinity to minus 1, union 1 to infinity. So that would be the domain of inverse secant. Okay. And then let me see here. Now I'm going to confirm one thing real quick. So let me look at something. Okay, all right. Yeah, so I wanted to confirm, I don't work with inverse secant too much, so I just wanted to confirm if I remembered the rule for data correctly, but it looks like I chose the wrong interval. Okay, yeah. So I kind of guessed it was minus pi over 2 to pi over 2, but instead they put a restriction on data as being between 0 and pi. Instead. And then I suppose because secant has a vertical asymptote at pi over 2, that we have to remove pi over 2 from that interval, okay? So then actually the range, which I got wrong, so that's actually going to be between 0 and pi now. And I guess at 0, I can include these if these aren't vertical asymptotes either. So then for arcsecant, it should actually be 0 to pi over 2 for the range, but then union pi over 2 and then up to pi. Okay, there you go. Okay, and so you could define different inverse trig functions with different ranges, but the standard convention for arcsecant is to choose this for its range. Okay. Okay, all right. No, so secant has, so the secant itself, right, not the inverse function. Secant has a domain of like, you could say that the secant is all real numbers, excluding all the places where it has its vertical asymptotes. So let's talk about that, I suppose. So I drew the picture of secant earlier, so let's go back to that picture real quick. Okay. Yeah, so the domain of secant is all real numbers except for all the places where it's going to have these vertical asymptotes, okay? So this secant function, if you look at it, it's not a one-to-one function, right? You guys remember what it meant? I think you guys talked about it, right? What does it mean for a function to be one-to-one? Oh, okay, all right. Yeah, okay. Yeah, so one-to-one meant it passes that horizontal line test, and you guys might recall earlier in the semester when you guys talked about inverse functions that you need a function to be one-to-one in order to have an inverse, right? Okay, all right. Yeah, so you needed a function to be one-to-one in order to have an inverse. So secant is not going to have like an inverse that works for all numbers because it's not one-to-one everywhere, okay? So you have to restrict your attention to like a portion where it is one-to-one. So for inverse secant, the decision was to restrict attention to this little strip between 0 and pi, or whoops. Yeah, my picture is a bit off, isn't it? Okay. I should redraw my picture a bit. Yes, I drew my picture kind of bad, and that's why it was confusing. I see. Yeah, because it has vertical tangents, blah, at the negative pi over 2's and pi over 2's. So it should have started like this. There you go. All right, perfect. And then the next one would have been starting down and opening down. Okay. That's why it was confusing. All right. Okay. So then for inverse secant, what we do is we look at this little strip between 0 and pi. Okay. And in this little strip, the secant function will pass the horizontal line test. So we can define an inverse function like over this little strip. Since that was between 0 and pi, that's why for inverse secant, I guess its range turns into 0 and pi. And then we excluded the pi over 2 because of the vertical asymptote there, okay? Okay. But then you could, in theory, choose a different strip and get a different inverse as well. But for like the Arctangent function, we choose to work with that strip between 0 and pi, okay? All right, any questions about that? Nope. Okay. So then let's finish up with the last two. So I guess you guys wanted to see the inverse cosecant and then inverse cotangent. Okay. All right. So then just again, thinking about what do the inverse trig functions do? So all the inverse trig functions, again, what they do is they output an angle. So for inverse cosecant, it outputs the angle theta, for which cosecant of theta will equal that x value. And then again, we have to put some kind of a restriction on the angle theta. So judging from what arcsecant was, this one probably will be minus pi over 2 to pi over 2, but then removing 0 since you'd have a vertical asymptote there, okay? All right. So then that range on the angle gives us the range of the function. So it would be between minus pi over 2 and pi over 2, but you would exclude 0 in the middle because it has an asymptote there, or cosecant had an asymptote there. Okay. And then as for the domain of the arc cosecant function, so its domain would be whatever the range of the original cosecant function was. And so it would be the same as the inverse secant function. So everything from minus infinity to minus 1, as well as everything from 1 to infinity, like that, okay? Okay, so that's inverse cosecant. All right, and then lastly, we'll talk about the inverse cotangent. Oops. Okay. So then inverse cotangent of x will output the angle theta, for which cotangent of that angle equals x. Okay, and then we'll have to put a restriction on this one. So since cotangent was cosine over sine, due to pi, so probably theta would be restricted between 0 and pi. Although I think that's another one that I'll have to double check as well. Okay. Yeah, all right. So yeah, for inverse cotangent, the decision was to restrict theta between 0 and pi. So then that tells us the range. Okay. And then as for the domain, so it would be similar to inverse tangent, so its domain should be all real numbers. Okay? All right. Okay, so then that covers the domain and the range for each of the inverse trig functions. The domain of each of them, you can kind of figure out by looking at the range of the like regular non-inverse trig function, okay? So if you know all the ranges of all the ordinary trig functions, you can get the domains of all the inverse trig functions. As for the range of each of the inverse trig functions, you're going to have to memorize the range for each of them. Because in a sense, the range is somewhat arbitrary for them. Like there's more than one right answer, if you will. So we had to decide somewhat arbitrarily on which answer we wanted for the range, and this is what we've chosen for each of them, okay? Okay. All right, any questions about any of that? All right. So then I guess I'll open it up to everyone again. So what would you maybe like me to cover next? Let me see here. Okay, sure. So Let's look at just the last part of the review, which is solving some trig equations. Are there any particular parts that you'd like me to focus more on, or any of those problems you want me to focus more on? Okay, let's look at C first. Okay. All right, so in that problem, we had the equation 2 sine squared x minus 5 sine x equal to 3, okay? And so in order to solve for x in this equation, so here, this is an example of sort of like a quadratic trig function. Yes, all right. All right, so let's look at this one first. So we have a quadratic trig function, trig equation here. So the way that we approach this type of question is we do want to treat it as if it were a quadratic for the moment. Yeah, so we'll start by moving the 3 over to the other side, as we would do for any quadratic equation, so that we can have it set equal to 0. And then next, you would want to try and factor this the way that you usually try to factor a quadratic in order to solve for its roots, okay? So then do you guys see how you would maybe factor this expression? Okay. Well, let's see. So we're going to try and factor it right now. Oh, so if it helps. So it might be kind of difficult to see right now because the equation involves sine, but if you maybe just replace sine with like a sort of a temporary dummy variable for the moment. Okay. So here, instead of writing sine, I'm just going to pretend that was just some variable u. And then like sine squared would have been like u but squared. So then for the moment, you can sort of pretend this is what you had. How would you factor this quadratic here? Okay, I think you had the right idea. So let's take a look at that. So in order to factor it, okay. No, that's all right. Yeah, okay. So yeah, in order to factor it, let's see here. 2u, and then you want minus 3 at the end, so minus 3 plus 1. Okay, and then you'd have minus 6 plus 1 to give you the minus 5, okay? Right, okay. So then here we factored it. And so what's the idea once you factor it? Well, you got a product equal to 0. So the only way the product would equal 0 is if one of the factors was 0. So there's two possibilities from this. Either 2u plus 1 is 0, or u minus 3 is 0, right? Okay, but here I think what it might be good before we continue, and remember that u was just a temporary placeholder for sine of x. So I think it might be good at this point maybe to switch back to sine of x in place of u, just so we don't lose track of the original problem. Okay. All right, so then there's possibilities. So here, sine of x would have to be equal to -1/2, and over here, sine of x would have to be equal to 3. Okay. Let's start with this one first. So can you guys think of any values of x for which sine of x would equal 3? Okay. So that's a little bit of a trick question because sine of x, right, can never actually be equal to 3. Yeah, okay, right. So again, remember that the range of the sine function was between -1 and 1. So it could never get up to 3, okay? All right. So that's one thing that you would maybe want to be a little bit wary of when solving trig equations. Depending on like the numbers in the problem, getting an equation that has no solution is possible, okay? Okay, but for this problem though, that was not the only possibility. We had another possibility that sine of x would equal -1/2. Okay, yeah. So sine is 1/2 at an angle of pi/6, but you want it to be -1/2, so you need to get the pi/6 angles in the third and fourth quadrants where sine would be negative. And so yeah, it would be 7 pi/6 would be the angle in the third quadrant, as well as 11 pi/6 would be the pi/6 angle in the fourth quadrant. Now, then of course these are not the only solutions because you know that if you go around the circle again, you'll get another solution, right? Okay. So if you want to sort of list out what all of the solutions are, the idea would be that if you add any multiple of 2 pi to either of these two solutions, then you would get another solution because that would have been like going around the circle a certain number of times. Yeah, okay. So you would add 2n pi or maybe 2k pi, n or k, whichever one you choose to use, would be representing like any integer. So then these sets of solutions would have been the solution to our original equation, okay? So then I guess a quick summary is if you got a quadratic trig equation like this, you want to start by factoring it like a quadratic. Once you've factored it and you've set each of the individual factors equal to 0, then there's a little bit of just needing to know like the values of your trig functions to solve the equation at that point. So like to get from this to this is where you just kind of have to know the answer sort of based off your knowledge of the sine function, okay? All right. So yeah, there was another request to look up J in part 3, so let's do that one next, okay? So what we had was cosine of tan inverse of 4. So we want to come up with an exact expression for this quantity right now. So let me start with the expression inside of the cosine first. Okay. So we have inverse tangent of 4, okay? So let's recall how inverse tangent works. So inverse tangent of 4 should be equal to an angle theta, okay, where tangent of that angle would be equal to 4. Okay. Furthermore, for the inverse tangent, we talked about it earlier, there's a restriction on theta for inverse tangent that it would be between minus pi over 2 and pi over 2, okay? Okay, now, for some of these types of problems, based off your knowledge of tangent, you might immediately know what the angle would be. If it were like one of those nice angles, a pi over 3 or a pi over 4 or a pi over 6 kind of thing, right? But 4 was not one of the nice values of tangent. So therefore, we don't know exactly what this angle is, theta, that will satisfy this equation, because it's just not one of the nice angles that we know. So there is something that we can do, though, which is the following. That wouldn't help too much, unfortunately. So I guess maybe real quickly. So the only nice values of tangent that we know are, so just focusing on angles in the first quadrant. So tangent of 0 is 0. Tangent of pi over 6 was root 3 over 3. Tangent of pi over 4 was 1. And then tangent of pi over 3 was root 3. And then tangent has the vertical asymptote at pi over 2. So these are essentially the only like sort of nice values of tangent that we know, at least focused on the first quadrant. So we don't know the angle that would correspond to a value of 4, okay? So when you have a number that's not nice like that, there's something else that you can do instead, which is the following. What I'm going to do is I'm going to draw a picture right now of a right triangle. Okay. And inside this right triangle, I'm going to label one of the angles as theta. Okay. Now, do you remember how tangent is related to the sides of a right triangle? Ah, okay, okay. All right. So you guys might remember that tangent of an angle in a right triangle was equal to the opposite over the adjacent. Okay, right. So what we're going to do first is we're going to label, thinking of 4 as being 4 over 1, okay? We're going to label the opposite edge of the triangle as 4 and the adjacent as 1 right now, okay? All right. From here, yes, we would use the Pythagorean theorem to figure out the hypotenuse. So here the hypotenuse would be the square root of 4 squared plus 1 squared, should give us the square root of 17 for the hypotenuse, okay? All right. So then once we figure out this lengths of the sides of this triangle, yeah, going back up to here now, we want the cosine of this angle theta. Okay. Okay, so based off the triangle, right? Cosine we know was adjacent over hypotenuse. So we take the adjacent of 1 over the hypotenuse of square root 17, and then that would have been the exact value of the cosine of the inverse tangent of 4. Okay. And then, so to me, that's a perfectly good answer. I know some people insist on like rationalizing, I think they call it the denominator. So you could also write the answer as square root of 17 over 17 as well, okay? So to me, either of these two would be acceptable to me. All right. All right, good. All right. Any other questions? Oh, okay, let me see here. The key said something else. Right, okay. That's good to know. I see, yeah. Yeah, so then I guess that would have been an incorrect answer on the answer key then. Okay. All right, so then I will fix that. The answer key, all right. Yeah, so I don't know if I did something funny like 4 plus 1 is 5. Or maybe that was like from a question that I had previously, and then maybe I changed that question but forgot to change the answer. So that happens a lot as well when I'm creating these. Yeah, okay. Mm-hmm. So I would say, so I think that sounds to me like a sort of personal kind of strategy thing, right? Yeah, okay, no problem. Right, right. Mm-hmm. Yeah, so it's definitely important that you know exactly, right, right, okay. So yeah, you do need to know the um, domain and I guess in particular range for all the inverse trig functions in order to answer questions like this. So to me, it's kind of, would it be helpful to shade in the circle? That's sort of like, would it be helpful to you for you to shade in your circle, right? So like, if that is helpful to you, then you should definitely do that. Right, okay. So everyone maybe has a different way though, of how they would see these things and how they would memorize these things. So it's kind of like, I would say it's kind of whatever works for you, you should do that, okay? All right, great, no problem.